Hey everybody, it's Thursday, March 25th, and as you can see here in the aim today, our goal for today's video is all about how we can describe oscillatory motion. That's it guys, we did it. We made it to the last unit of the year. It's been a long road, but we finally got here. Now, what I hope you'll realize as we go through this unit is we've actually learned a heck of a lot of stuff this year. The reason why I bring this up specifically in the context of this unit is because this unit, more than any other one in this course, I think, is really a synthesis of a lot of the concepts that we learned so far this year, and I will continue to bring these up as we move along. The main thing that you should remember about these kind of problems, these oscillatory motion kind of problems, is that it really does build upon every single thing that we've talked about this year. And so that's an important thing to keep in mind going forward. Now, what we're going to be doing here in this video, and even in the next one, is talking a lot about definitions. Because oscillatory motion is a kind of motion that we've never really seen before. And so we are going to need a lot of new pieces of vocabulary to be able to describe it. And so that's really the main focus here for this video, is to talk about the framework that we use to analyze oscillatory motion. Now, of course, one of the first things that we have to talk about here, which should be a surprise to nobody, is we really definitely want to nail down exactly what is oscillatory motion, because this comes up a lot. Now, we'll say here, when an object experiences simple harmonic motion, the object is said to be oscillating. Now, I'm sure some of you are looking at that and you're thinking, well, what is simple harmonic motion? Now, simple harmonic motion actually has an extremely simple, straightforward definition. But because we're not quite there yet, I'm not going to formally define it for you. We have to build in some other things first. What we should say is that for now, you can think of oscillatory motion as a synonym for simple harmonic motion. And a lot of times when I refer to simple harmonic motion, including in the name of the packet, I will refer to it as SHM. So when an object experiences simple harmonic motion, the object is said to be oscillating. Now, of course, the question here is, well, what does oscillating mean? What does the word oscillation mean? You've actually seen this before. I want you to think about when you've seen the word oscillation before, because you have seen it before. And the main thing that you should remember is that exactly in the context in which you've probably seen it, it means the same thing in this context. When I was first asked this question when I was taking Physics 1, where have you seen the word oscillation before? The first thing that popped into my mind was on the fan in my house. When you push the little button on the fan that says oscillate, what does it do? It starts turning back and forth. And that's exactly what an oscillation is. An oscillation is a motion back and forth between two extremes. That's what an oscillation is. And so this kind of motion is the kind of motion we're going to be looking at all unit long. An object simply moving back and forth between two extremes. Now, of course, we want to talk a little bit about this two extremes part. This idea, the fact that it's moving back and forth between two extremes, should be giving you some idea that the location of those extremes is actually something that's going to prove itself to be very important. That location, the location of the extremes, has a specific name, and that name is the amplitude. So the magnitude of the object's maximum displacement from its original or equilibrium position is called the amplitude. The amplitude is the magnitude of the maximum displacement. Now, just to be very clear, although we will formally define this in a bit, we'll just say here at first, the symbol for amplitude is A. And of course, because it's a magnitude of displacement measurement, the unit here is naturally going to be given in meters. Now, something that should be noted about the amplitude before we move on is that since the amplitude is defined as the magnitude of the object's maximum displacement from the equilibrium position, it is always recorded as being positive. You never say the amplitude is negative blah. You just say the amplitude is blah, whatever the number happens to be. And that number, again, is a measurement of how far the object ever gets away from the equilibrium position, the farthest location, the maximum displacement. Take a second to pause this video and write this down. And when you hit play, we'll take a brief look at an oscillating object just so you can have a good mental picture.
Here we have an object hanging from a spring. As you can tell, it's fluttering around a little bit because it's very unstably precariously balanced here on this pen, which is wedged between this folder of papers and my shelf. But besides the fact that it's, wobbling around a little bit, you can just go ahead and ignore that. The basic idea is this thing is in equilibrium, and it's not going to begin to oscillate until I displace the object, which is these keys here, from its equilibrium position. And so notice when I displace the keys, they start to oscillate. The reason why we are saying they're oscillating is because their motion is pretty straightforward. They are moving back and forth between two extremes, up, down, up, down, up, down.
So the classic example of an oscillating object is an object moving back and forth while it is attached to a spring. A spring, by its very nature, causes an object that is attached to it to oscillate. And so whenever we are talking about oscillatory motion or simple harmonic motion, the object on a spring is going to be an extremely prominent example of this kind of motion. I want you to keep that in mind as we're going forward. Now, what we want to do here for a pretty good part of this video is we want to be able to describe the motion of an object that is experiencing oscillatory motion. And the first thing that we have to do when we are trying to describe the motion of an object is we really just want to talk about where it is, right? What its position is. I don't want you to lose sight of this as we're going forward, because I feel like in the past, when I have shown what I'm about to show here, like over the course of the next 15 minutes, it does take a little bit. Usually halfway through, somebody will raise their hand and ask, like, wait a second, what the hell are we doing? The point is, when an object is experiencing simple harmonic motion or oscillatory motion, we'd like to be able to describe that motion. Hello, that's what physics is, right? The point is, when we are trying to describe an object's motion, talking about things like its position and its velocity are very important things. That's what we're doing. We're trying to describe the object's position as best we can. Right now, I'd actually like you to write that down. Let's try to describe the object's position and velocity. Now, what I'd like you to do here is actually pause. I want you to write this down, what I just wrote here in the pen on the left side, and then I want you to draw this image. It is a little bit annoying to draw. Do not try to draw a person. It's a waste of time. Draw the person as a dot. Do not go nuts about drawing the springs. Show the top of the spring, show a little straight line down, and then just zigzags. That's good enough. And then draw the person as a dot underneath. But it's crucial for the purposes of this part of this for you to draw all 6 of these positions like this. Take a second to pause this video here and do that. And when you hit play, we'll move on. Now, it should be obvious to everybody that if we are trying to describe the position and the velocity of an object, it's a smart idea to just look at it, right? Because the position of an object is literally just where it is. And so we can see when an object is experiencing oscillatory motion, moving back and forth between two extremes, notice it's at one of the extremes above the 0 line or the equilibrium line. Here, it says it's at its amplitude. And when it's at the farthest point below the equilibrium line here, we say it's at its negative amplitude. Notice, of course, the reason why we are saying it's negative amplitude is because the amplitude is always reported as a positive number. And so if the amplitude is, let's say, 2 meters, then we're saying that this is y equals negative 2 meters because this 2 meters happens to be below the x-axis on the graph. And so the first thing that we're going to do here, which I hope is really going to drive home a very important point, is the first thing that we're going to do is we are literally just going to plot the position of the object on a graph. And so notice at this first time here, time 1, the object is located at a vertical position of y equals 0. At 2, it's up at its maximum positive displacement, so we'll just put it about there. At time 3, or whatever instance 3 here, the object is back at its equilibrium position. Notice it's just moving back and forth between its equilibrium positions, or between the amplitudes, passing through the equilibrium position. At instance 4 here, it's at the lowest part, and we should make this symmetrical because it's supposed to be symmetrical, and so we'll say that should be about, let's call it here. Then at position 5, the object gets back to its equilibrium position. And then at position 6, it's up here again at the positive amplitude. So besides that errant pen mark from a moment ago, I hope you see where this is going. The object is oscillating back and forth between two extremes. And if we're trying to draw this graph as a position as a function of time, again, hopefully you see where this is going here, it takes a familiar shape. Now, obviously, this is not an excellent drawing. It's not just because I'm trying to do this with the digital pen. It would kind of look bad like this on a classroom board as well. But the idea is this graph, a graph showing you the position as a function of time, should take a very familiar shape. The shape of this graph we often refer to as a sinusoidal graph. And so sometimes we refer to these oscillations as sinusoidal oscillations. Now, sinusoidal is an adjective. And that word, just to be clear, it refers to when objects experience oscillations which can be described by sine functions or other trig functions. Notice whenever you are watching a medical show, which I'm sure you all have at one point, they say like, he's back in sinus rhythm. When they say sinus rhythm there, they're talking about the sinusoidal oscillations of a heart, right? Because your heart compresses when it beats, right? It squeezes and then it unsqueezes, and squeezes and then it unsqueezes. So essentially what it's doing is it's moving back and forth between two positions. Its smallest position when it's fully compressed and pumping out that blood, and then its biggest position when it's filling up with blood. That's the idea here. Sinusoidal oscillations refer to objects when they are moving back and forth between two extremes. Take a second to pause this video here and make sure you have this graph sketched. Try to do it better than I did. Make it actually look like a sine curve, and then write down that definition of sinusoidal. And when you hit play, we'll move on. So here we have it, a graph of the object's position versus time. Now, of course, building on what we did at the very beginning of the year, we would also like to be able to draw a graph of the object's velocity versus time. Now, luckily, we spent a good amount of time at the beginning of the year talking about how we can draw one graph from another graph. And so that's what we're going to do here now. This is a graph of position versus time. How can we use a graph of an object's position versus time to find information about the object's velocity? Now, if you were just thinking in your head, slope, well, it's curved. What am I supposed to do? We have to look at the slope of a line that is tangent to the curve. That's the idea. And so I'm going to draw all over this position versus time graph that I have at the top to make the point. But if we just take a look at the slope of a line that is drawn tangent to the curve, we can start to see how it's going to map out. We have first a positive tangent line, then a zero tangent line up here at the maximum displacement or at the amplitude. And I think that should make a lot of sense to everybody. Here, the thing is traveling up and up and up until it gets to as far as it's going to go, and then it turns around and comes back down. Well, at the turning point, or in other words, when it reaches its maximum height, it's got to stop before it turns back around. So it really should make sense to you why the velocity is going to end up being zero here, because the slope of the tangent line is zero there. When it's on its way back down here, we have a slope of a tangent line with a negative value. Then again, at the lowest point, just like for the highest point, it's turning around, so the slope of the tangent line is going to be zero. Then we got a positive slope of the tangent line, and then zero again. And so the point is, we are using the information about the sine of the slope of the tangent line to get a good idea about what our graph is going to look like. And so we have a positive velocity because we have a positive slope of the tangent line here, then zero, then negative. And again, we want to try to make this symmetrical, then zero, then positive, and then back down to zero. And so hopefully you see the idea here. Notice once again, we have another familiar looking shape. The only difference between this curve for the velocity and this curve for the position is that this curve starts at zero, meaning it's best described by a sine. And for this curve, it starts at 1. So it's best described by a cosine. And that's the idea. When we literally apply graphing tricks from the beginning of the year, we see that the position, the velocity, and of course, if we did it for the acceleration too, it would work out. They'd be described by trig functions. Notice here for the velocity, the slope of the tangent line here would be 0, then negative, then 0, then positive, then 0, then negative. And so the acceleration graph would look like basically like a negative sine graph. And if you're in calculus, that should make a lot of sense to you. If you're not in calculus, just ignore this part. It really doesn't matter for this course. This is just enrichment for the calculus kids. Velocity is the derivative of position, right? And so if you've learned your derivatives of your trig functions, then it should make sense that the derivative of sine is cosine, and so that's why the velocity is described by a cosine. And if you take the derivative of a cosine, well, that would be the negative sign, and that's why the acceleration is described by a negative sine curve. Pretty cool. Now, before we move on to a more formal mathematical approach to how this is done, there are two more terms we'd like to define here very quickly. And those terms are period and frequency. Now, what we talked about quite a bit when we were talking about circular motion was the term period. Now we're going to bring frequency into the fold. Hopefully you will realize why they completely apply to simple harmonic motion. The period definition is that it is the time it takes for an object to complete one full cycle, or in other words, the full series of changes, or one complete oscillation. What we mean by that basically is that the object moves through all possible positions. So it starts at 0 like we just had in that particular instance. It goes through all of the positive positions, through all of the negative positions, and then back down to 0. That's what one full period looks like. It always has one part of this curve, which we generally refer to as the peak, and one part of this curve, which we generally refer to as the trough. Now, we usually only do that in the context of waves, but it applies here too, because that's ultimately what the graph looks like. When a wave is traveling through space, the particles of the medium are experiencing oscillatory motion. And so that's why there's a lot of parallels there as well. This is what one full period or one full oscillation looks like on a graph. The period, actually, though, is a measurement of the time that takes. So basically, it's a measurement between here and here. It's how much time. The frequency, on the other hand, a similar definition, is a measurement of the number of cycles or oscillations experienced by the object each second. There's a lot of similarities between those definitions that I think you should realize. Period is a measurement of the number of seconds per cycle, the time it takes for one full cycle, and frequency is a measurement of the number of cycles per second, or how many cycles per second. Now, of course, based on that, we can very easily write equations for these quantities. Before we do that, though, of course, I'd like you to write down these definitions. So take a second to pause this video here and write that down. And when you hit play, we'll move on. So let's go ahead and mathematically define period and frequency. The symbol for period, as hopefully you remember from circular motion and rotational motion, is uppercase T. It's a time, but it's a special time, so it gets capitalized. And the equation we can write two ways. We can say it's the number of seconds over the number of cycles, but of course, because the number of seconds can be more normally defined as just the time, we can write time over the number of cycles. And so if we know that it takes 10 seconds to do 10 cycles, well, we take our time, 10 seconds, divided by 10 cycles, and we find out that it's 1 second per cycle. It's the number of seconds per cycle. Frequency, on the other hand, is the number of cycles per second. And so that means we could take the number of cycles divided by the number of seconds. And so for that same example, if we have 10 cycles in 10 seconds, then we would take the number of cycles 10 divided by the number of seconds, 10, and we would get 1 as well. Of course, the difference here is going to be the unit. So the time is measured in seconds, and the number of cycles is literally just a number. There's no unit. The period is measured in seconds, because it's seconds divided by something with no unit. But the frequency is measured in a unit called hertz. Now, it's important to realize here, 1 hertz is defined as 1 inverse second, or 1 over seconds. It's important to realize, and you'll see the similarity here in a minute, this is a lot like radians per second. Yes, we write down the unit sometimes as radians per second, but whenever we treat it mathematically, we treat the radian like a 1. It's the same thing with cycles. Well, first of all, cycles isn't even really close to a real unit. It's just like a counting measurement, but still, mathematically, it's treated by a 1, because obviously an inverse second is a stupid thing to say and is very annoying. We named it after a famous physicist, Heinrich Hertz, who did a lot of work with oscillating radio waves. And so it gets the name, the hertz, abbreviated capital H, lowercase z. It's also important to realize for that unit, the case is very important. It must be a capitalized H and a lowercase z. Take a second to pause this video here and write that down. And when you hit play, we'll move on. One more important note before we fully move on from this here, it's important to realize since the period is a measurement of the number of seconds per cycle, and the frequency is a measurement of the number of cycles per second, they're the inverse of one another. And so we can say here, period is 1 over f, or obviously if we wanted to solve that for the frequency is 1 over t, t standing for period here because it's uppercase. The fact that frequency and period are inverse quantities is super important in this unit. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, now we've gotten to the part of this unit where things can get confusing. The main thing I want you to remember as we're going through this is we are trying to describe the position and the velocity of oscillating objects. Yes, we said we can put them in a graph and notice that the graphs look like sine and cosine functions, but we'd like to be able to use an equation to describe the motion of the objects. Now, an important thing to recognize here, I think, is that it's really hard to describe the motion of an object attached to a spring like that. And the reason why it's very hard is because the size of the force exerted by a spring is proportional to the amount the spring is being stretched. And while the object is experiencing oscillatory motion here, you can see the spring is stretched different amounts. And so the fact that the object not only has a force acting on it, and so it is accelerating, but it has a force on it which is continuously changing size, it becomes very complicated to fully describe the motion of these objects. And so what we do is we recognize that we've actually already seen something pretty similar to simple harmonic motion in terms of an object moving back and forth. And the thing we've seen that's very similar to simple harmonic motion is uniform circular motion. And so here's a video I've had saved on my computer for years. I really like this video. The point of this video is to try to show you the similarities between simple harmonic motion and circular motion. The main idea is that exactly in the same way an object experiencing simple harmonic motion, it moves back and forth and back and forth and back and forth between these two extremes, the same thing is happening to an object moving in a circle in each direction. Notice horizontally, it's just going from here, then over to here, and then back and forth horizontally. Vertically, it's doing the same thing. It might not seem like it because, well, of course, because you're just looking at it moving in a circle, and so it seems like it's moving horizontally and vertically at the same time, which it is. But what I like about this video is that when you think about rotating the circle and just looking at the object head on, then you can really realize in the y direction, it goes up, just like the spring, it comes down, and then it goes back up. Now, notice they're not fully turning this circle because they want you to see that what they've done is rotated it, but that's the basic idea. The x coordinate and the y coordinate of an object moving in a circle just goes back and forth between these two extremes. And because we have already pretty nicely defined the motion of an object moving in a circular path, we can apply everything we've said about the motion of an object in a circle, again, to try to mathematically talk and describe about the position and the velocity of an object experiencing simple harmonic motion. That's the goal. So what we're going to do here is we're going to take a look at an object experiencing circular motion, and we are going to try to fit it into our picture of an object experiencing simple harmonic motion and see what we can get out of it. And so basically what we're doing here is we're going to describe an object moving around a unit circle. Now, usually in a unit circle, the radius of the unit circle is 1, but what I'm going to do here is what I'm going to say is, well, the farthest the object is ever going to get away from the midpoint here is going to be the radius. And if we're also talking about the farthest the object ever gets away from its equilibrium position, notice here is the equilibrium position for the y and x coordinate. In the y direction, the object is just going to be moving like this. So we can say this is the equilibrium position, and it's just going up and down and up and down. And for the x direction, it's just going up and down like that. But here's the equilibrium position. We can say, well, the farthest it's ever going to get away from the equilibrium position is just the radius of the circle. And so for simple harmonic motion or oscillatory motion, we refer to that maximum displacement from the equilibrium position as the amplitude. Let's go ahead and call that the amplitude here. So we're going to call the radius of this circle the amplitude. And we're going to say this object, as it's moving around the circle, has experienced an angular displacement, which we'll call theta. And so we can describe how this angular position is going to change using the equation theta equals omega times time. Remember, the angular velocity is equal to delta theta over t, and so by solving that for delta theta, and here we're just dropping the delta and calling it theta, if we want to solve that for theta, we get theta equals omega times t. Notice this is the rotational equivalent of distance equals speed times time. So that angle, theta, is described as the product of the angular velocity and the time. Now, of course, we can write an equation for the angular velocity from this equation, and we can say, well, yeah, that's going to be delta theta over time. Not that complicated. It's just a basic relationship from rotational motion. And we could say, well, what is a cycle for an object moving around a circle? This whole time we've been talking about period is a measurement of a number of seconds per cycle, frequency is the number of cycles per second. What the hell is a cycle for an object moving in a circle? And the idea is a cycle for an object that's moving around a circle is when the object moves around the circle once. When an object moves around a circle once, its angular displacement is 2 pi. And when an object moves around a circle one time, since that's the time for one cycle, we can call that the period. Now, of course, we can rewrite this equation by saying this equation is really just 2 pi instead of divided by the period. We could just say it's multiplied by 1 over the period. And here's the deal. We said earlier that the period is the inverse of the frequency. And so that means the frequency is the inverse of the period. And so since we have 2 pi multiplied by 1 over t, well, we can say here, since 1 over t is the frequency, we can just call this 2 pi f. This is an extremely, extremely important relationship in this class, that our notion of the angular velocity from rotational motion can be related to the frequency of an object, which is just moving back and forth in a straight line. This is very important. Now here, instead of calling that angular velocity, we call it angular frequency. And we're going to call this just a regular old frequency. And the important thing to realize here is that usually we measure this in radians per second, but remember, we treat the radian mathematically as a 1, and so the unit is 1 over seconds. And for regular frequency, well, that's really a measure of the number of cycles per second. But because the cycle is a unitless thing, we treat that as a 1 as well. And so the whole point here is that we can relate these two quantities, essentially, because they're measured in the same unit. Essentially, what we're doing here is we're taking the frequency measurement, which is a measurement of the number of cycles for an object moving back and forth in a straight line, and by multiplying it by 2 pi, we rotationalize it. And this picture is kind of stupid, but I like it because it draws the comparison. Notice here how these measurements evolve for the angular frequency and the frequency. Now, this isn't given the symbol f down here. This is a symbol for frequency that we use in upper level physics. It's a Greek letter called nu, but let's just pretend it says f. It's measuring out here the number of cycles and the number of radians. Notice when the number of cycles gets to 1, you can see how it goes again here. When the number of cycle gets to 1, this is going to get to 2 pi radians, or 6.28. Notice, though, the ratios are always the same. The difference between the omega and the frequency is that you just have to take the frequency and multiply it by 2 pi to get the omega. That's the deal. Because one rotation can be considered to be one cycle, we can draw comparisons between these. All right, now we're almost there. Remember, the point of this is so we can get a mathematical description of the motion of an object experiencing oscillatory motion. We're almost there. Remember your Algebra 2 trig material. For a unit circle, we use trig functions to define the y and x coordinates. In fact, that's where the trig functions ultimately come from, or at least their definitions. And so for a unit circle, the y coordinate is described by the sine function. Now, generally, it's just the sine function because the radius of the unit circle is 1, but because the radius of our circle is the amplitude, it's being described by a sine theta. Notice here, just do it. This is the y-coordinate. Sine is opposite y over hypotenuse, a. And so when we solve it for y, we get a sine theta. For x, and I'm sure you guys know this here because you've taken 2 years of physics, that's the adjacent side. We're going to use cosine, and we're in business. Now, of course, hopefully when you see this, you will have an answer to the question of why the heck we spent time talking about this omega here, because we can write the angle theta now in terms of omega. And so instead of writing a sine theta, we can write a sine omega t and a cosine omega t. And of course, because omega is equal to 2 pi f, we can rewrite this further as a times sine of 2 pi f times t and a times cosine of 2 pi f times t. Notice what these equations say is if we want to find either the x position if the object happens to be oscillating back and forth horizontally, or the y position if an object is oscillating back and forth vertically, we can use this equation to write a position as a function of time for the object. Meaning, if we know the amplitude of the oscillation and we know the frequency of the oscillation, we now have a function of time. So if we want to know, say, where the object is at 5 seconds, we plug in 5 seconds for our time, and boom, it spits out the x coordinate automatically. And that's pretty cool. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So let's just go ahead and formally introduce these equations here. I want you to write this under the heading position and velocity function for an object experiencing oscillatory motion. As we just said here, the y-coordinate is given by the equation a sine theta 2 pi f over t, and the x-coordinate is given by the equation x equals a cosine 2 pi f over t. Now, we would like to write equations for the velocity as well. Now, as it turns out, really, to come up with these equations, you need calculus. Those of you who are in calculus, if you've learned the chain rule, then you'll understand why these look the way they do, because again, the velocity is just the derivative of the position function. And so, in a nutshell, what the chain rule says, right, is to take what's on the inside, bring it out to the front, at least for this trig function. And so our velocities look like this. The y velocity is going to be 2 pi f times the amplitude times the cosine 2 pi f times t. And for the x velocity, and again, we're just going to give the magnitude here and not go nuts about it, it's 2 pi f a sine 2 pi f t. And we'll just write here magnitudes. The reason why we're only talking about the magnitudes and we're not going to go nuts about this is because these functions are always changing sign. And so basically the time and the frequency and amplitude measurements are going to take care of that on its own. And it is the case in all of these equations that a is the amplitude, f is the frequency, y is the y position coordinate, x is the x position coordinate, vy is the y component of the velocity, and vx is the x component of the velocity. These equations are functions of time, meaning if we know information about the frequency and the amplitude, we can plug that information into these equations and then always know where the object is in the case of these two equations and how fast the object is going in the case of these two equations. In that sense, it's a really smart idea to think of them as templates. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, so very quickly before we move on to 2 questions before we wrap it up for today, because I know in a lot of ways this has been a lot of new material for today, I just want to show you those 2 equations in the reference table. The first equation that's related to what we've talked about today in the reference table is the template for the position function. You really should be thinking of this as a template. What I mean by that is when you are asked to write a function of the position as a function of time, you should be using this to do that. You figure out what the amplitude is, you plug that in there. You figure out whether it should be a sine or a cosine, and you plug it in there. And then you figure out what the frequency is. Now notice what I just said here is you figure out whether it should be a sine or a cosine. You can do that. It's obvious. If it starts at 0, it's a sine. And if it doesn't start at 0, then it's a cosine. That's it. You'll be able to tell when you look at it. And we're going to do a bunch of examples of these over the next couple days. The other equation that's in the reference table is the relationship between the period and the frequency and the angular frequency, all in one equation. So notice here, in exactly the same way, we said that omega is equal to 2 pi f. Well, we can also say, well, the frequency is the inverse of the period, and so that means really it's 2 pi times 1 over t, or 2 pi over t. Now, obviously, this is solved for t, so it's showing 2 pi over omega, but that's the basic idea. Let's take a look at a problem. This problem here, which is in the simple harmonic motion packet, page 31, number 6, says the displacement of a harmonic oscillator is given by y equals 3.4 sine 25t, where the units of y are meters and t is measured in seconds. Find the amplitude and the frequency. Go for it. Give it a shot. Pause this video here. What is the amplitude? What is the frequency? And when you hit play, we'll go over it. Okay, so our function here in this problem is y equals 3.4 sine 25t. So the first thing you need to realize is that the reference table gives you a template. The template says x equals a cosine 2 pi f times t. What that equation tells us is that the number in front of the trig function is the amplitude. So that means in this problem, for part A, the amplitude is 3.4 meters. Now, notice here an important point. When we usually write these, we leave off the units because it is implied that the unit is meters. Now, also notice that they say that the unit of y is in meters, and the only way that this could be measured in units of meters is if this is measured in units of meters. That's an important point. The second thing we'll say for B is that the template of this position function tells us whatever is multiplied by the t inside the argument of the trig function, well, that's 2 pi f. The thing that's multiplied by the t in the argument of this trig function is 25. So that means 2 pi f is equal to 25. And so notice in solving this for the frequency, all we have to say is that the frequency is going to be 25 over 2 pi. And so that means the frequency, and I'll just write this over here, is going to be 3.98 hertz. And that's it. Take a second to pause this video here and write that down. Maybe give a little summary note about how the fact that we're saying this is a template, how that really works. And when you hit play, we'll move on to the last question for today. Okay, last question for today, page 31, number 3 in the SHM packet. It says figure P11.3 shows the displacement of a simple harmonic oscillator as a function of time. Part A says find the period, frequency, and amplitude of the oscillator. B says at what time does the acceleration have its largest positive value? And then C says when does the acceleration have its most negative value? Take a second to pause this video here and try out just part A. And when you hit play, we'll go over it. So for part A here, to figure out the period, you got to look at the graph. Because remember, we said here, the period is the amount of time it takes to complete one cycle, or to go through all of the positive positions and then all of the negative positions and get back to the equilibrium position. That means the period here is 4 seconds. Notice we can also measure the period from peak to peak. So notice 1 to 5 is also 4 seconds, or from trough to trough, 3 seconds to 7 seconds is also 4 seconds. So for part A, the first thing we'll write here is that the period is 4 seconds. The second part says the frequency, and well, that's pretty straightforward because as we've already mentioned here, the frequency is the inverse of the period. And so we're looking for the frequency, and we know now that the period is 4 seconds. So the frequency is 1 over t, and so that means this is just going to be 1 over 4 seconds, or 0.25 hertz. Notice what those two measurements mean. I think it makes sense. It says it takes 4 seconds to complete one cycle. That's the period. Well, if it takes 4 seconds to complete one whole cycle, then that means each second we're only getting a quarter of a cycle. First second we get a quarter, second second we get a quarter, third second we get a quarter, and the fourth second we get another quarter cycle to make one full cycle after 4 seconds. And the last part of this question asks us to find the amplitude. Now, as you can see here in this question, the graph is given to us. The amplitude is defined as the largest displacement, the maximum displacement, or at least the magnitude of the maximum displacement from the equilibrium position. And so notice the equilibrium position is marked at 0, and so the amplitude here is 10 centimeters. Since we traditionally report these things in meters, we're going to go ahead and say that's 0.1 meters. No cm, just meters. Okay, let's go back to parts B and C. Parts B and C ask you at what time does the acceleration have its largest positive value or its most negative value? I want you to give this one a shot at your own. Come up with an answer for the times, come up with an explanation for the times, and when you hit play, we'll go over it. Part B is asking us at what time or times does the acceleration have its largest positive value? Acceleration is the time rate of change of velocity. The acceleration is going to have its largest positive value, and we'll write a note about this here in a little bit. The acceleration has its largest positive value when the velocity is changing from a negative value to a positive value. And so that happens down here at the troughs. We'll say for part B, the answer is 3 seconds and 7 seconds. So for part B, t equals 3 seconds and t equals 7 seconds. And I'll write here in parentheses, most negative position, comma, most positive acceleration. For part C, it's basically going to be the reverse of that. The acceleration has its most negative value when the velocity changes from positive to negative. And so that's going to be at 1 and 5 seconds. So for C, the answer is t equals 1 second and t equals 5 seconds. And I'll write here in parentheses, the most positive position is the most negative acceleration. Now, notice we are answering this from the standpoint of just like graphing techniques. Tomorrow, we're going to talk about a different method for analyzing an object in simple harmonic motion, and I really think this point is going to make a lot of sense. We're going to come back to this point again tomorrow. For now, take a second to pause this video here and write that down, and when you hit play, we'll move on. All right, so quick note there. For now, we're going to say the maximum positive acceleration occurs when the velocity changes from negative to positive, and the maximum negative acceleration occurs when the velocity changes from positive to negative. And so I'll just handwrite another note here very quickly. The maximum positive acceleration occurs at the max negative position. And for the maximum negative acceleration, I'm going to say that occurs at the max positive position. Take a second to pause this video here and write that down. And when you hit play, we'll take a look at one last thing before we go for today. All right, for the last thing I'd like you to do for today, look at this graph. Look at it. Maybe it's hard to really fully get a sense of. So let's get everything out of there, or at least most of it. Write a function for the position as a function of time from this graph. Give that a shot. You're going to have to do this in this course. Look at a graph like this and write the function. Based on everything we've said so far here in this video, you should be able to do that. Take a minute to pause this video here and write the position function as a function of time for this object. And when you hit play, we'll go over it. According to the reference table, there is a template for the position as a function of time. A cosine 2 pi f times t. In order to write the function for the position, you need to do a couple things. Is it moving in the x direction? No, it's moving in the y direction. So we'll write y. Honestly, if you write x, though, it doesn't matter. It's okay. It's the same thing. Then the template says the first term there should be the amplitude. The amplitude is 0.10. You could write meters. You could not write meters. Let's just write meters here. What the heck? Then it says to write the trig function. So we write a cosine. Psych. Remember, you always have to think about whether it is a sine or a cosine. Here, this graph starts at 0. So it should be a sine. You really want to make sure that you remember when you're using that reference table template, you have to decide whether it's a sine or a cosine. Then we have to put 2 pi times the frequency. Well, as we said here, 2 pi times the frequency, well, that's going to be 2 pi times a quarter because the frequency is 0.25 hertz. And so notice when we take 2 pi times 1/4, then really what we have is 2 over 4 pi, or pi by 2, a half pi. So we'll put pi over 2 times t. And that's it. Now notice if we go to Desmos, the online graphing calculator, then we see exactly what we just saw in that graph. Notice it goes up, down, and back again by 4 seconds. Pretty cool. Now, unfortunately, it's hard to set the window for the y and the x-axes on this calculator program, but the idea is you can actually do this on your Texas Instruments graphing calculators or Casio if you have one. You just have to make sure when you're doing this graph to put it in radian mode because you're putting this pi over 2 thing in there, because otherwise it's going to give you the wrong graph. We'll talk about that, though, in the future as we're moving along. And with that, that's it for today. Have a good one, everybody.